This is a 2D simulation region with a slab of negative index material at the center. The negative index material has been set up using the magnetic electric Lorentz material model, and if you're interested in knowing more about it, see the link to the bulk metamaterials example linked below. Start by adding the source by clicking on the arrow next to the Sources menu and selecting Gaussian. Edit the source. We will use the Gaussian beam profile. Set the injection axis as x-axis and keep the injection direction as forward. Set the angle theta property to 30 degrees. Under the Geometry tab, set the x position to -3 microns, the y position to -2 microns, and the y span to 20 microns. The z parameters don't apply since the simulation region is 2D. Under the Beam Options tab, set the waist radius to 1 micron and the distance from focus to -4.25 microns so that the focal point of the beam is in front of the source injection plane near the surface of the negative index slab. Click on the Visualize Beam Data button to see the plot of the field profile over space. You can see that the beam is contained in the span of the source region and it's not being clipped at the sides. Since the wavelength of the beam is 0.5 microns, the beam waist diameter that we have set is 4 times larger than the wavelength, so the scalar approximation should be appropriate. However, if there's any uncertainty about whether the scalar approximation is valid, it's best to first test the source by running the simulation with just the beam propagating in free space with no structures. You can then check the resulting beam profile to make sure that the distance from focus is as expected and that there is little backward scattering at the injection plane. Light getting scattered at the source injection plane indicates that there are source injection errors, which could occur when the scalar approximation is not valid. Right-click and disable the negative index slab structure and run the simulation. From the profile monitor, I can see that the focal position of the beam is near x equals 0, which is what I want. Right-click and visualize the transmission result from the monitor behind the source. This shows that there is less than 0.01% of power being scattered backwards. Next, to demonstrate what you would see if the scalar approximation is not valid, switch back to Layout and edit the beam setting. Set the waist radius to 0.25 micron. Now, the beam waist diameter is the same as the wavelength, so it's in the range where the scalar approximation starts breaking down. Run the simulation and check the transmission in the backward direction. Now I can see that more than 3% of power injected is being scattered backwards, and that indicates that the scalar approximation is breaking down. Now go back to the original setup. Switch back to the layout mode and change the beam waist radius back to 1 micron and re-enable the negative index slab object. Now run the simulation and plot the E-field profile from the profile monitor. You can see that the beam diffracts to a steeper angle away from normal when it enters the negative index material, as expected. Next, we'll go over some general tips to keep in mind when simulating a Gaussian source. We want to make sure that the field profile of the beam doesn't get cut off at the sides by plotting the beam profile before running the simulation. The beam profile can be truncated if either the source span is too small or the source injection region intersects with the simulation region boundaries. Before running the full simulation, we can run a simulation with the source in free space to make sure that the desired beam is injected. If using the scalar approximation, we can gauge whether the approximation is valid by using a monitor behind the source to measure the amount of backwards scattered power like we did in the demonstration, or another method is to use a monitor in front of the source and check the transmission in front of the source to see how much the magnitude of transmission varies from the expected value of 1. The Gaussian beam has a well-defined polarization direction. To represent an unpolarized beam, or a circular polarized beam, you can run 2 simulations with orthogonally polarized beams and sum the results as a post-processing step. Some detailed examples showing how to simulate an unpolarized beam and circular polarization are linked below. To represent a different beam profile other than Gaussian or Cauchy-Lorentz, the import source can be used to specify a custom field profile. The import source will be covered later in this section.